Today we're going to finish Unit 8, Acquisition 1. We are going to focus on this last bullet point, calculating rates of reaction. So first, what is reaction rate? In the lecture from yesterday when we did kinetics, we said that reaction rate is the speed in which a reaction occurs. So when a reaction occurs, our reactants are being converted to products. So reaction rate is going to be the change in concentration of reactants or products per unit time. Since we're looking at how the concentration of our reactants and products change over time, our units are usually going to be molar per second. Whenever you see something in brackets, that just represents our molarity or concentration. So as a reaction proceeds, two things are going to happen. The reactants are going to get used up. And since the reactants are getting used up, that means their concentration is going to decrease. Well, as those reactants are getting used up, products are being formed. So that means the concentration of our products are going to increase. So let's look at what this would look like if we were to graph how the concentration of our reactants and products changed over time. So at the start of our reaction, we're going to have all reactants. Before the reaction begins, I don't have any products. And what happens is over time, if we were to measure the concentration of our reactants, the concentration is going to decrease. Those reactants get used up in order to make products. At the start of my reaction, I don't have any products. But over time, the concentration of those products are going to increase. So I normally call these fish graphs because they kind of look like a fish. So those will be our fish graphs. When we express rate or when we calculate rate, we can do it one of two ways. We can either look at the rate of disappearance of the reactants, so we can calculate how does the concentration of reactants change over time, or we can express it as the rate of appearance of the products. So we could also calculate how does the concentration of our products change over time. All right, so here is our equation for rate. To calculate the rate of reaction, we are going to take the change in concentration and divide it by the change in time. One important thing to note, for rate of disappearance, we will place a minus sign or a negative sign before this equation to indicate that the concentration is decreasing. So rate is always expressed as a positive number. All right, so let's look at our first example. So let's say we just had a very simple reaction, A is producing B. So kind of like we saw on our little graph up here, I could see that the concentration of my reactant, A, is decreasing over time, and the concentration of my product, which is B, is increasing over time. So let's work on number 1. Calculate the rate of appearance of B over the first 20 seconds of the reaction. So to calculate rate, we're going to take the change in concentration. Remember, delta means change. And we are going to divide by the change in time. All right, so we want to calculate the rate of appearance of B over the first 20 seconds. So at 20 seconds, the concentration of B is 0.46 molar minus the concentration of B at 0 seconds, which is 0 molar. All right, I can calculate the change in time by taking the final time minus the initial time. And I would get 2.3 times 10 to the negative second molar per second. All right, let's try another one. Number 2, calculate the rate at which A disappears over the time interval from 20 seconds to 40 seconds. So again, rate is going to be equal to the change in concentration divided by the change in time. So I'm going to look at the change in concentration of A from 20 seconds to 40 seconds. So normally when we're calculating the change in concentration or change in time or change in anything, we normally do final minus initial. So I'm going to take the final concentration minus the initial concentration and then do the same thing for time. 40 seconds minus 20 seconds. 1.2 times 10 to the negative second molar per second. All right, next example. I know we probably thought we were done with stoichiometry, but stoichiometry is coming back, but it'll be much simpler this unit. Next example, the rate of formation of oxygen is 0.0084 molar per second. Calculate the rate of disappearance of N2O5, dinitrogen pentoxide. All right, so we're going to start, as always, with our given, 0.0084 molar per second of oxygen. And all we have to do for these types of problems is plug in the mole ratio. I can see that my dinitrogen pentoxide is going to disappear twice as fast as oxygen is formed. So all I have to do is put in my mole ratio. Remember, the mole ratio comes from the coefficients from our balanced reactions. And then again, whenever we are setting up any conversions, it's always important that we set up so our units are going to cancel or our substance are going to cancel. So since my given is oxygen O2, oxygen needs to be in the denominator. And I would get 0.017 molar per second. So that just means that N2O5, my dinitrogen pentoxide, is going to disappear twice as fast as oxygen is going to appear. Next problem, we're going to do it the exact same way. So again, we always start with our given. 6.0 times 10 to the negative fifth molar per second. And that's of oxygen. And then all we have to do is plug in our mole ratio from the balanced reaction. Oh, sorry guys. All right, so that would get me to 4.0 times 10 to the negative fifth. All right, next problem. So this problem is nothing new, but we're going to calculate the average rate for 3 different intervals. So for the first one, we're going to calculate the rate between 0 and 10.5 seconds. and then we'll do another rate between 10.5 and 22.3. And then lastly, we'll do the last one from 22.3 and 35.7 seconds, because we want to see what's going to happen to the rate of reaction as this reaction proceeds. All right, so rate for our first reaction. This is going to be the rate of disappearance. I see that as time goes on, concentration of A is going to decrease. So I'm just going to add that negative sign because rate always needs to be positive, and the negative sign just indicates that the concentration is decreasing. All right, so again, it's going to be change in concentration divided by change in time. So I'm going to take my final concentration, maybe, come on, of 0.0045 minus the initial concentration for that first interval. And then I'm also going to do the same thing for time. I'm going to take the final time of 10.5 seconds minus the initial time of 0 seconds. And I would get 4.8 times 10 to the negative fifth molar per second. All right, we can calculate the rate for my second interval. So again, I'm going to do the final concentration, 0.0040 minus the initial concentration, 0.0045, divided by the change in time. (22.3 seconds minus 10.5 seconds. And this would get me 4.2 times 10 to the negative fifth meters per second. And then we're going to do the same thing for the third interval. So my final concentration of interval 3 is 0.0035 molar minus the initial concentration, 0.0040 molar, divided by the change in time, 35.7 minus 22.3, gets me 3.7 times 10 to the negative fifth molar per second. All right, so what I want you guys to do is look at the rates for each of these intervals. So rate over the first interval was 4.8 times 10 to the negative fifth. For the second interval, 4.2 times 10 to the negative fifth. And for the third interval, 3.7 times 10 to the negative fifth. So what do we notice about the rate of reaction? Hopefully you see that the rate of reaction decreases as the reaction proceeds. So why do you think that occurs? Why would the rate of reaction, I don't know how to get rid of that little g, that's just going to stay there. The rate of reaction decreases as the reaction proceeds. Why do you think that would occur? Well, the reason that this is going to happen is because as the reaction proceeds, the concentration of the reactants decreases. That goes back to our little fish diagram. So again, reactants decrease, the products increase. So as the reaction goes on, the concentration of the reactants goes down. So that means there's less reactants available. That brings us back to collision theory. The less reactants we have, the less collisions can occur. The less collisions we have, the slower the reaction is going to occur. So as our reaction proceeds, as we go from that first interval to the second interval to our third interval, we see that the rate of reaction decreases. The reason that it decreases is because we have less reactant molecules available. All right, very quickly we're going to talk about instantaneous rate, but luckily for this class you will not have to calculate it. So instantaneous rate is the rate of reaction at any given moment of time. So far we've been looking at the average rate of reaction. What is the average rate over 10.5 seconds? If I wanted an instantaneous rate, I want to know what is that rate at exactly 600 seconds, for example. The way that we would calculate this is you would have to draw a line tangent to the curve and then calculate the slope of that line. For this class, we're not going to do this, so we're just going to focus on average rate. As always, work on your mastering chemistry. Email me with questions. Sorry for all of the glitches. I promise I will get better at these screencasts as we go on with our e-learning days. See you guys later.